Assalamualaikum warahmatullahi wabarakatuh and a very good day. My name is IRFAN bin Muhammad SOFIAN, alongside with my team members Muhammad SOLEH bin Abdul Majid, Muhammad SYAFIQ bin AZHARI, PHIRAPHONG AWAD. Today we're going to present about SKIP2113, Design and Analysis of Algorithm Group Project. Okay, so moving on to the table of content of this slide. Okay, we're going to the problem solving case, which our problem solving case is the knapsack problem. Then we're going to show you the design technique, where we use dynamic programming and brute force, and we will show you each of them, the algorithm, the runtime analysis, and the comparison. Okay, so the problem solving case that we have is how to maximize the total profit by selecting items to fit into a knapsack with a weight capacity of 8 kg. The weights and profits of the available item are as follows. So the weights that we have is 3 kg, 4 kg, 6 kg, and 5 kg. So the profit is for 2 units, 3 units, 1 unit, and 4 units. So there are 4 items in total. So determine the optimal combination of items to include in the knapsack to achieve the maximum profit while ensuring the total weight does not exceed 8 kg. Okay, so the design technique that we're going to be used to solve this knapsack problem is that we are going to use dynamic programming and brute force, where we're going to be explained later in a bit more depth in the slide below.
I'm Muhammad Saleh bin Majid, and now I will be presenting on one of the techniques we use to solve the problem, which is the dynamic programming. For the first step, based on the problem, we will list out the given data. So now we list out the weights as the 3465 and the profits 2314. And we remember that the rule or the knapsack limit is the weight must not exceed 8. Then we can proceed to the next step, which is to categorize each weight and profit as an item. Here we have 4 items since we have 4 pair of weights and profit. For example, we have the first item, the weight is 3 and the profit is 2, until the final item, which is the weight 5 kilograms and the profit as 4 units. Before we proceed, remember that the specific cell DPIJ, that the maximum profit for the first items with a knapsack capacity of J, which means that the weight I minus 1 is the weight of the current item, and the profits I minus 1 is the profit of the current item also, and J refers to the current knapsack capacity. After that, we can do the next part, which is essential for dynamic programming, which is to create the dynamic programming table. But before that, we have to know certain rules. So for the calculation of each cell in the table, we assume dp, ij, I for row, and j for columns. So when the weight of the I minus 1 is greater than j, then the specific cell will copy down the value from the row above. And if it is lesser or equal to j, then the cell will do the calculation based on the max between the dp I minus 1j and then the profits I minus 1, and then we add on the dp I minus 1 and for the column j minus weight for the I minus 1 also. For the table here, we have set the column as the weight of the knapsack itself and the row as the weight and the profit, or we can say value of the item. And what we can do now is that we can fill all the row, the first row, which is 0, no item, no weight, no value. We can fill it out as zeros for all the row. And then For the column 0 until 2, we also can fill out with the zeros since all the items carries a weight 3 or more. So that anything with the weight below 3 cannot be filled out in the cell, which we end up with the DP00 row, all zeros, and DP00 until DP02, all zeros also. Next, we fill out row by row. So for the row after the 0th item, which is the item 1, weight 3 kg and profits of 2 units, we can see here that since we only consider the first item, from the 3rd column until the 8th column, we fill out with only the value of the first item, which is 2 units. Next, we consider the second item where the weight is 4 kilograms and profit is 3 units. As we can see here, from the column 0 until 3 is still the same, but starting from column 4 and 8 is different. So we can say that the DP2 for the column 4 until 6, it is replaced by 3. And why is that? Because the second item can fit the knapsack for the limit 4, 5, and 6. So we will maximize the profit by having put the second item with the profit 3, and that's why we get 3 for all the column from 4 to 6. And why is it that the knapsack limit 7 and 8 is 5? It is because the item 1 and item 2 are both combined, since it can fit the limit from 7 to 8. As we can see, if we put on the total weight, it will be 7. So the knapsack limit 7 and 8 can maximize the profit up until 5. Now we have the third item with the weight 6 kilograms and profit only 1 unit. And we can see here that for the third item row, there are no changes. This is because although the weight is high, it will lead to a low profit, and we cannot fit it the units into any of the columns to increase the profits. Hence why it remains the same value. Finally, for the fourth item with the weight 5 kilograms and profits of 4 units, we can see that the changes only occur from the knapsack limit 5, 6, and 8. Why this happens is the same as before. It is because on the knapsack limit 5 and 6, we can pick the fourth item. We consider compare it to all the other items. The fourth item can give us the most profit for these two limits. As for the knapsack limit 8, we can maximize the profit by combining two items, which is item 1 and 4. And that will lead us to the value of maximum profit 6 units. Now on to the final step, which is to compare the result to find out the best combination of the maximum profit. So since the limit is 8, first we will compare the last row column, which is the maximum profit of 6, and with the one from the row above, which is the profit of 5. And when we compare, we find out that DP48 is greater than DP38, which means that item 4 will be included in the best combination. We can do the same for the DP3 and 5. We observe that the maximum profit with item 1 is only 3 kilograms. So since the DP48 is greater than DP35, we can conclude that item 1 was also included in the best combination. In a nutshell, the best combination to achieve maximum profit while not exceeding 8 kilograms is 6 units. So the first item being 3 kilogram with a profit of 2 units, and item 4, the 5 kilogram with a profit of 4 units. When we calculate it again, the weight is exactly 8, means it does not exceed 8, and the profit remains 6 units, which is 2 plus 4. As to why dynamic programming is chosen to solve this problem, it is because the efficiency in solving optimization problems. As we can see here, we can avoid having overlapping sub-problems and achieving optimal substructure, since we iterate each item with different capacity constraint, which will lead to an optimal solution, ensuring the maximum profit. By avoiding redundant computations, DP will offer us a scalable and reliable solution.
Assalamualaikum warahmatullahi wabarakatuh. My name is IRFAN bin Muhammad SOFIAN, method number 288181. Okay, so now I'm going to explain about my part, which is the dynamic programming algorithm. So as you can see, this is the code for the dynamic programming algorithm, which is the function to solve the knapsack problem and return the maximum profit function knapsack, which is weight, profits, capacity, and number items. So we're going to run through this algorithm step by steps. So the first thing that we're going to do is define the problem. So as you are given an array of item weights, so we're going to give it a value weights, an array of item of profits, so we're going with profits, and the knapsack capacity, we're going to give it the variable of W max and the number of item, which is N. So after that, we're going to create a 2D DP table. As you know, the core idea of dynamic programming is to break down the main problem into a smaller sub-problems and solve each sub-problems only once, storing the solution in a table to avoid redundant computations. So in this case, we'll use a 2D array called DP, where DP IW, which represent the maximum profit that can be obtained by considering the first I, which is item, with a knapsack capacity W. So that is where we got DP in bracket I in bracket W again. So initialize the base case. We start by initializing the DP table for the base case. The base cases are when no items are to consider, where I equals to 0 or when the knapsack capacity is 0. So in this case, the maximum profit will be 0 for the base case. So after that, we're going to fill up the DP table using the recurrence relations. So to fill up the DP table, we use a nested loop. The outer loop iterates over the items, which is I, from 1 to N. So the inner loops iterates over the knapsack capacities, which is W, from 1 to W max. So for each item and capacity, we use the recurrence relations to calculate the maximum profit that can be achieved. So the condition weights in bracket I minus 1s lesser than equal to W will be checked if we can conclude the the number of item in the knapsack without exceeding its capacity. If so, we consider two choices: either exclude the number of in the iterations item and take the maximum profit from the previous row, or include the number of item and add it to profit to the maximum profit obtained from the remaining capacity. And next, we're going to find the maximum profit, where once the DP table is filled, the maximum profit that can be achieved using the knapsack is stored in the DP table, where DP in bracket N in bracket W max. So after that, we're going to backtrack to find the included items. So to determine which items were included in the optimal solution, we can backtrack through the DP table that been filled. So starting from the DP in bracket N in bracket W max, which DP and W max, we check if the value is different from its previous, which is dp n minus 1 w max. If it is, it means that the nth item was included in the optimal solution. So we add the index n minus 1 to the list of included items and reduce the knapsack capacity by weights in bracket n minus 1. So we repeat this process until we reach the first row of the DP table. Okay, next is the dynamic programming time complexity. So the time complexity of the dynamic programming algorithm for the 0-1 knapsack problem is O in bracket n times W max, or to simplify it, O in bracket n times W. So this represents the upper limit on how the algorithm's running time grows concerning the input size. So in the context of the knapsack problem, where n is the number of items and W max is the knapsack capacity, the primary factor influencing the time complexity is the process of filling up the DP table, as we refer to the previous algorithm. So consequently, the overall time complexity of the algorithm is O n times W max. So it is essential to consider that the time complexity is directly related to the size of the problem. As the number of items or the knapsack capacity increases, the running time of the algorithm will grow proportionally. The algorithm performs well for small moderate problem sizes, effectively solving the knapsack problem.
All right, so now for the second approach, we will be looking at the brute force approach. Now, what is brute force, you may ask? Well, brute force is finding every possible solution based on the problem statement and definitions of the concept involved. This means there is no definite formula to solve every problem by using brute force, but more of brute force acts as a principle where you find every possibility for the problem itself. So in this case, in our knapsack problem, our knapsack 01 problem, we have to find every possible combination of items that can exist with the parameters given. The parameters being 8 kilograms is the maximum amount of weight that our knapsack can carry. And since there are 4 items, the total amount of combinations that can exist is 2 to the power 4, or in other words, 16 possible combinations. Now, how can we use brute force to solve our problem? First things first is we have to simplify the question itself. So from our question, where we have 4 different items, we can put them into a table with weight and profit in the other 2 columns. So as you can see, item 1, 2, 3, 4 has their weight 3465 and profit 2314 respectively. This also can be done in an array form with weight W equals to 3465 and profit or P to 2314. And we also have to denote the parameters, which is the total weight of the knapsack that can carry. It has to be 8 kilograms or less. Now for the second step, we have to find every possible combination between our 4 different items. So as we said before, there will be 16 possible different combinations, and as you can see on screen, there are 16 different possible combinations. Now in this array, 0 means an item is not taken, while 1 denotes that the item is taken. However, if you look closely, these numbers can also be quite reminiscent of binary, specifically 4-bit binary. So in order for us to solve this problem very efficiently, what we can do is we take a 4-bit binary where each bit will represent each item. We can do from 0000, and we can basically count up to 1111 using the binary system. By doing that, we'll get all 16 possible combinations. Now for the third step, what we have to do now is basically tally up the weights and profits based on the 16 possible combinations that we found out just now. So if 0001, it just means that item number 4 will be chosen and weight will be 5 and the profit will be 4 as seen in array number 2, 5, 4. So if we tally up every single possible combination, we'll get this specific array. And from here on out, we will be able to solve the problem in the next slide. For the fourth and final step, we'll be choosing the highest profit. Now, how do we do this? We basically have to go through the whole array again, but we have to find out which combinations will go over our parameters, and then from the combinations that still follow our parameters, we can then choose the highest profit. So first things first, we have to see which combinations go over our parameter, which is anything that goes above 8 kilograms. So as you can see, 11 combination number 4, 11.5, where 11 kilograms and 5 profit points. 11 kilograms is much, much higher than 8 kilograms, so it goes over our parameters. So we will mark it as red in color to basically denote that it's going to be discarded. So by then discarding all of the combinations that go overboard, we can see that 00546143328675 all are less than 8 kilograms. But out of all these combinations, combination 8 and 6, or either I should say combination number 10, with 8 kilograms and 6 profit points, is the only combination that has the highest profit points out of all of these. So by doing so, we indirectly have found the highest profit following the parameters of our question. So now in conclusion, our brute force approach will give us the result where combination of item 1 with weight 3 and profit point 2 and item 4 with weight 5 and profit unit 4 would give the highest profit value of 6 with a total weight of 8 kilograms, making it the best combination out of all the 16 possible combinations that still falls under our parameters and also gives us the highest profit points. Now, why was brute force the approach that we used for this specific question? Now, one of the reasons is it's very easy to implement. If anything, brute force is one of the first things that people would think of to solve a problem like this. Next is it also goes over every possible combination, which is very the characteristics of brute force. So people would feel a bit more safe as you wouldn't miss a single possible combination or possibility itself. However, as we know, or as we're going to know later on, brute force is a exponential type growth in terms of time complexity, where it would equal to 2 to the power of n. However, as this is still a very small problem with only 4 items, or in other words, n equals to 4, it is still very much manageable, and if anything, it's still very efficient compared to maybe some other algorithms out there. So for all these reasons, this is why we use the brute force approach for this specific question.
Hi, my name is PHIRAPHONG and I will explain about the algorithm for brute force. So the function Knapsack brute force takes two parameters. Item, which is a list of tuples representing items, each containing weight and profit, and max capacity, which is the maximum weight, the knapsack whole. The function initializes variable best combination and max profit, which will store the combination of items and the maximum profits found so far. The function then iterates through all possible combinations of items using binary representation. The outer loops runs from 0 to 2 power of number items minus 1. The number of iterations will be 2 power of number items, as each item can either be included 1 or not included 0. Within each iteration, a new combination list, total weight, and total profit are initialized to keep track of the current combination properties. The binary representation of the current iteration number is used to determine the items included in the current combination. The inner loop iterates through each item index j and check if the jth bit of I is set to 1 using bitwise AND comparison. If it is, the item included in the combination and its weight and profit are added to the total weight and total profit respectively. After the inner loop, the current combination weight and profit are checked to see if it's valid, total weight small or equal to max capacity, and if it's maximized, the profit seen so far. If it's thus, the best combination and max profit are updated with the current value. After all iterations, the next set items are generated based on the best combination. It filters out the best item that are included one and created a list of tuple containing the weight and profits of the included item. The functions return three value: best combination, which is a binary representation of the best combination; max profit, which is maximum profit obtained; and knapsack items, which is a list of tuples representing the item included in. So in this problem, so if we run the code with the item and max capacity of 8, So it will print the best combination, maximum profit and item included in the knapsack, and the output is the best combination is 1001, which means the item 1 and item 4 is picked, and the maximum profit is 6, and the item included in the knapsack is the 3 and 5 weight, total of 8, and the 4 and 2, which is the maximum profit of 6. Let's take a look in the time complexity analysis for the brute force approach to the knapsack problem. In the brute force approach, we generate all possible combinations of items and evaluate each combination to find the one that maximizes the profit while staying within the weight constraint. As discussed earlier, the number of possible combinations is 2 power of n, where n is the number of items. For each combination, we need to calculate the total weight and total profit, which takes n times as we iterate through our n items to compute the sum. Therefore, the overall complexity of the brute force approach is the product of the number of combinations and the time taken to evaluate each combination. So time complexity for the brute force is O 2 power of n multiplied by n. You can see the time complexity grows exponentially with the number of items n. This exponential growth made the brute force approach highly inefficient for large instance of the knapsack problem, which is time consuming and impractical for the large problem.
Okay, so now we're going to compare between the two techniques that we use to solve the problems, which is the knapsack problems. So the technique that we use is the brute force and the dynamic programming. So we're going to compare each of two of these with their approach. So brute force uses the approach of enumerate all possible subsets of items, while dynamic programming break problem into smaller overlapping subproblems. So the method that brute force uses is a recursive solution with nested loops, while dynamic programming uses recursive solution with memorization, which is top to down, or iteration, or both, which means bottom to up. So for the time complexity of brute force is O in a bracket 2 power of n, while dynamic programming is O in bracket n times W max. For the space complexity, brute force is O in a bracket of n, but the dynamic programming is O in a bracket n times W max, or just O in bracket W max. It is depending on the implementation. So for the efficiency of the brute force, it is inefficient for large values of n, while dynamic programming is efficient for moderate to large values of n and W max. Okay, so next will be the overlapping subproblem, where brute force does not utilize overlapping subproblem, but dynamic programming utilizes the overlapping subproblem and stores the solution in the DP table. Okay, so between these two, the redundant computation, brute force perform redundant computation for subproblems, while dynamic programming avoids redundant computation through memorization or DP table. For the optimal substructure, brute force relies on optimal substructure to find the best solution, but dynamic programming utilizes optimal substructure to find the best solution. So the advantages of a brute force is it is simple to implement, and dynamic programming it is efficient for larger problem instances. But disadvantages for the brute force is it is inefficient for large inputs, exponential time complexity. But dynamic programming, the disadvantages is requires more memory for the DP table, and it is complex to implement.
I will continue for the comparison. So for small instance, the brute force approach works well for small problem size, but its efficiency declines rapidly as the number of items or n increases due to its exponential time complexity. Dynamic programming remains efficient even for small problem size, providing an optimized solution without suffering from exponential growth in computation time. For moderate instances, as the problem size increases moderately, the brute force approach becomes impractical and inefficient due to its exponential time complexity. Dynamic programming shines for moderate problem sizes, efficiently handling subproblems and avoiding redundant computations, making it a choice. As for large instances, brute force is highly inefficient and not recommended for large problem sizes, especially when the number of item n or knapsack capacity W max is very large. Dynamic programming can still be efficient for larger problem sizes depending on the specific value of n and W max, making it more suitable for real-world applications with significant inputs. In conclusion, dynamic programming offers a more scalable and efficient solution for the knapsack problem, particularly for moderate to large problem instances, making it the preferred choice in most cases. On the other hand, brute force is limited by its exponential time complexity and is only practical for our very small problem size. So that's all from us. Thank you for listening.